let's look at this technique of logarithmic differentiation. So we see the steps here, and we're going to work through this. The first example we're going to look at is a function we've actually already differentiated in this lesson. So this function 2x plus 1 raised to the power 5 times x cubed minus x plus 1 raised to the power 4. We've looked at this one before, and we saw that it required product rule and then a couple different chain rules. So there were a few different rules we needed to use in order to differentiate this thing. We're going to, instead, this time, we're going to look at this logarithmic differentiation technique. And so this is going to be a technique that sometimes is helpful. You don't always have to do this, but sometimes it's helpful, especially if your function has multiple products, quotients, or kind of compositions, exponents, things like that. So if there's a lot of pieces to your function, a lot of multiplication, division, exponents, things like that, log functions work great in trying to simplify the function down. And that's what this technique does. So step one, what's the first step for logarithmic differentiation? We're going to apply the natural log function to both sides. So step one, apply natural log to both sides. So we have our equation here. We're going to apply it to the left. So it'll be natural log y on the left. And then on the right, it'll be natural log of this entire thing. So 2x plus 1 raised to the power 5 times x cubed minus x plus 1 raised to the power 4. We've applied the natural log to both sides. That's step one. Step two, we're going to simplify the right side of our equation. And so when we look at this, the right side is pretty complicated. But what we have now is we have some product, we have a product, and then we have some exponents all inside this log function. So this is going to simplify down quite a bit. And this is where the log properties become helpful, is when we actually try to simplify down what we've done. All right, so step two, let's apply our log properties here. Nothing to do on the left, so that'll just stay natural log y. But on the right, the first thing we can do is deal with that product. So we have a product of two x terms in here. So we know when we have multiplication, when it's one thing times another thing inside the log function, we have a log property that allows us to convert that multiplication that was inside into addition that's outside. So this becomes the natural log of 2x plus 1 raised to the power 5 plus natural log x cubed minus x plus 1 raised to the power 4. So again, we use the property there that allows us to convert the multiplication that we have inside into addition outside. All right, so that is going to take care, we don't have to do product. If we're going to differentiate this, we no longer have to do product rule. That's kind of nice. Now, there is also, we now have these exponents. We have this raised to the power 5 in here, and we have this raised to the power 4. And these exponents are being applied to everything. So inside the log function. So for this first one, it's 2x plus 1 all raised to the power 5. So I can take that exponent and bring it outside the log function, and it just becomes a constant multiple. So this becomes 5 times the natural log of 2x plus 1. And then same thing over here. This 4, everything inside the log function is being raised to this power 4. So it's x cubed minus x plus 1 all raised to the power 4. So this exponent can come in front of the natural log there. So it becomes 4 times the natural log. And that was, again, the log property that allowed us to convert exponents inside into multiplication outside our log function. All right, so this is looking pretty good. And we want to see if there's anything else we can do with these log functions. So you keep simplifying down as far as you can go. And really, as soon as you get down to addition or subtraction, That's as far as you can go. You can't simplify it any further. So in this first one, there's this addition. So our main operation here is addition. We can't simplify this any further. Same thing goes for the second one. If we look at the second log term here, it's x cubed minus x plus 1. Really, the main operations are subtraction and addition here. We can't go any further. Yeah, there's an exponent, so there's this raised to the power 3, but it's not like this raised to the power 4. This raised to the power 4 was affecting everything. This cubed term is only on that 1x. So there's other things outside of that cubed. So in both of these, the main operation is addition or subtraction, and we can't simplify further. All right, so now we're ready for step 3, and that's to do implicit differentiation. So we're going to apply the derivative to both sides of our equation. So when we differentiate the natural log of y, well, we'll come back to that. This is where the implicit differentiation really comes in. But we're just going to differentiate everything now. So when we differentiate this log term, this is chain rule. We have to use some chain rule here, so we don't completely get away from our derivative rules. So we still need to do a little bit of that, but it's going to be easier. So it's 5 times, and we're going to differentiate our way through the log function. So it's 1 over whatever was inside the parentheses, so 2x plus 1. And then we take that inner term and multiply by its derivative. So this is, we're starting our derivative now. All right, so we've differentiated that first term. Now let's differentiate the second term. So that 4 is just a constant multiple, so that just kind of stays in front. Then we need to differentiate through our log function. So that's just 1 over what was originally inside the log function, so x cubed minus x plus 1. And then we take that inner function and we multiply by its derivative. So we're using chain rule here for both of these. So just the general log rule, as we sometimes call it. So we do the derivative of our outer log function first. So it's just 1 over what was ever inside the log function times the derivative of what was inside the log function. Same thing over here. 1 over what was inside times the derivative of the inner function. All right, so that's chain rule. Now what's going to happen on the left? So remember that we're doing implicit differentiation. We're doing implicit differentiation at this step. So whenever we differentiate a y term, we're viewing y as a function of x and as a variable. So this natural log y, we differentiate it like usual, we get 1 over y. But whenever we're doing implicit differentiation and we differentiate a y term, we then multiply by y prime. So the derivative, if we're differentiating our equation, we differentiate all the x terms like usual. So everything on the right side gets differentiated like usual. But then we have this natural log y, which is really where the implicit differentiation kind of comes in. So we differentiate the log function like usual, we get 1 over y, but then we multiply by the derivative of our inner function. Kind of like what we did over here and here. All right, so that's the implicit differentiation. Finish differentiating. So derivative of 2x plus 1 is 2. So I would multiply the 5 and the 2 together to get 10, and then we'll put those on top of the fraction here. And then derivative of x cubed is 3x squared. Derivative of minus x is negative 1. So we get a 3x squared minus 1 here. And I'll multiply that with the 4 and put everything on top, just to kind of clean this up as we go. So we're going to get a 12x squared minus 4 all over x cubed minus x plus 1. And so this is equal to 1 over y times y prime on the left. And so we're done with our differentiation. And now the very last step, step 4, is we want to solve for y prime. So it's almost done. It's almost done for us. We just have to get rid of this y. So the way we do that is we multiply y on both sides. And that's step 4. Step 4, just multiply both sides by y, and that's going to give us y prime. So we get y prime is equal to y times 10 over 2x plus 1 plus 12x squared minus 4 over x cubed minus x plus 1. And that's pretty good, but it's not quite done yet. We got a little bit more here. Our original function, it was y equals, and then all x terms on the right. And we want the same thing for y prime. We want y prime to equal just all x terms. So the very last thing we need to do is just replace this y. And we know what y is actually equal to. It's equal to just our original function. So we make that substitution in for that replacement there for our very last step. So we get y prime is equal to, let's fill in what we know y is. So it's 2x plus 1 raised to the power 5, x cubed minus x plus 1 raised to the power 4, 10 over 2x plus 1 plus 12x squared minus 4 over x cubed minus x plus 1. And there's our derivative, all in terms of x. So the differentiation part of this wasn't too bad. It was just we had to use chain rule a few times. And using the log functions here really allowed us to kind of simplify the differentiation process. We were able to simplify the equation down quite a bit, which was then easier to differentiate. All right, we're going to try a few more examples using this logarithmic differentiation, just for the practice. And notice we've already differentiated this function. And so you can go back and kind of compare the results. And it might not look exactly the same. So our result here probably doesn't look like quite like what we found before. But there's probably some factoring and simplifying we can do in either one to make the two match. So the answer you get from the logarithmic differentiation might not quite look the same as if you were to just go through the log or the derivative rules in order. But they're equivalent answers, so that's fine. The nice thing about log differentiation is, especially in this case, you end up with a nice, almost factored version of your derivative here. So it's a lot of the factoring's done for you. So we have this term here times this term. So this is nicely factored. And if we wanted to, we could combine these two fractions by getting a common denominator and maybe simplify this even further. But as is, this is a pretty good version for our derivative if we were going to go on and try to, say, figure out where the derivative was equal to 0. So logarithmic differentiation, not only does it kind of sometimes simplify the process, but the format of our answer also is sometimes a bit easier to work with if we were going to do more work beyond just calculating the derivative. All right, so we'll get to some more examples, but it's always a fun technique to try.